Hi, my name is Ross Majeski, and this video was designed to introduce undergrad students to our research work going on in the Visual Analytics and Data Exploration Research Lab, as well as our Department of Homeland Security Center of Excellence, the Center for Accelerating Operational Efficiency. I serve as the director for both of these centers. And so an obvious question to ask is, what is visual analytics? Well, visual analytics is using advanced analytical algorithms combined with interactive visual interfaces to help users explore data and analyses. And this allows for the combination of domain expert knowledge with advanced analytics and data exploration. So think of us as lying at sort of the intersection between AI, human cognition, computer graphics, and trying to create decision support tools for people. Some examples of the types of tools that we've created in the past include things like the Visual Analytics Law Enforcement Toolkit. So here you're seeing different types of crimes on a map. The dots here in the iPad version represent the different types of crimes. You see a calendar view where the counts per day are shown or the counts per hour are shown. We created tools for trying to route you around crime hotspots, looking at how to also optimize police patrol routes and these sorts of things. And we even did some fun exercises with different police units. For example, at Purdue, they asked us to examine drunkenness and public intoxication records with respect to football games. And so what I'm showing you here in this graph is just the number of public intoxication arrests per day for that year. Here I'm showing you Purdue's campus. And probably if you think about this for a little bit, you can guess where the bars are in this location. We have a big cluster of dots in that southeast corner, and that's the bar location at Purdue. We can also look at the time of day when most of the arrests occur, from midnight to sort of 3 a.m. And then we can also look at the arrests per day of the week. Now, the first thing you might think is odd about this is how many of these arrests occur on Sunday? And this goes back to these interesting questions of needing domain expertise. You know, we define a day from midnight, 12 a.m. to 11:59 p.m. But we can see all these arrests that are occurring Sunday from midnight to 3 a.m. Probably we would consider that Saturday night drinking. So we could think about how to adjust this time series. And then for fun, we wanted to think about how did these arrest reports correlate to things like football games, home and away football games. So here I've annotated our graph where the red dots that are filled in are the home football games, and the open red circles are the away football games. And you can see that we typically have spikes on home football games. There's more drinking, more arrests, and the couple red dots that aren't big spikes actually correspond to school holidays, Labor Day, fall break, those sorts of things. And then the question for fun was, you know, does winning or losing matter? So here we can see Purdue lost to Notre Dame. Here we can see Purdue won their homecoming match. Here we can see Purdue lost to Iowa. So it didn't really matter, right? We find that the patrons of our football games are happy to drink either way. You drown your sorrows or you celebrate your winning. But these were sort of some of the fun things we could think about doing with this data, and then even thinking about how we might use this to create public campaigns or to do counter programming for alcohol awareness at the campus. So lots of fun things. Other things we can think about could include gang boundaries and network geography. So you can imagine that in Chicago, where this data is from, I might know where all the gang locations are on a map. And for each gang location, I can create this sort of hotspot. So I'm looking at two gangs here. I've got the Latin Kings, their territory areas that we're seeing Latin Kings crimes in are in dark red. The Latin counts are in dark green, and this purple is sort of some computed overlap areas. There's high overlap between those gangs. We might think, well, there could be lots of violence in these overlap areas. But if we start thinking about, you know, those old analogies of wrong side of the track and stories like that, we can start saying, well, what if we add some network geography, looking at sort of the road networks and how crime might travel? And now that overlap area becomes smaller. And now what if we add those cuts about different highways creating natural boundaries between the data, or the river creating natural boundary? When I add those to the data, we can automatically separate these two gangs, so the overlap area goes away. And it turns out that these are sort of sister gangs in the area. And we've done lots of geospatial analytics sorts of work. We've worked with the Coast Guard to create different patrol routing. Here we're showing search and rescue cases and trying to think about how fast we can rescue these. And underlying all of this is really this idea of space, time, and exploring these sorts of notions. And that's what my lab has really been successful about, is trying to think about how we can couple data mining and AI techniques to support these interactive things, looking for patterns, anomalies, and all sorts of things. But what's also interesting is we can have a lot of fun with big data. We can think about what interesting questions could we ask a data set. So let's take, for example, what's in a name? Shakespeare said, what's in a name? That which we call a rose by any other name would smell as sweet. And we can play this game of trying to map last names to the US map. I can get your last name from a phone book, and it has an address associated with it. So we can link all of this data together. And we had the Montagues here. We had Capulets and Montagues and Romeo and Juliet. So the Montagues are primarily East Coast name. We see sort of Virginia, North Carolina. And then we can even create a word cloud showing you what names are similar to this in terms of spatial distribution. So like Wilson and Pettit have similar spatial distribution. We tried this for Capulets, but there were very few Capulets in the phone database. But the phone book and census data can be stored in MySQL. You have 78 million records, 1.7 million unique surnames. And the reason why I also mentioned census data is because now if I know where you live, we can do things like get sort of income locations for that block level. We can go to Zillow and see how much your house is worth. So we can start associating other sorts of factors with different names and asking all sorts of questions like, how much is my name worth? And you can try out our application at our demo.vaderlab.org/name website. And here you can see my last name, Majeski. And there's a very clear Polish belt in the US. If you know anything about Polish immigration, Chicago is a huge Polish hotspot, one of the largest Polish populations in the world. You see New York City, areas around sort of Detroit, Detroit, Cleveland, those places. So you see this Polish belt, and you can see the names that have similar spatial distribution to my last name are also Polish surnames. So kind of interesting and fun things to think about. We can play this game for income as well too. So we can try to look at how much do we think that a Majeski surname is worth. And then we can also start asking our questions, well, where would French surnames be? So Moreau is a popular French surname, and we can see that the two hotspots for Moreau are New York and Louisiana. And not surprising, right? New Orleans, we associate this with French culture. We can see other French surnames having a similar distribution like Mercier, Robillard. So just fun things we can think about doing and exploring in these different spatial temporal data sets. And this was actually done by some undergrads that joined the lab too. So thinking about how we can get graduate students and undergraduates working together have been a core tenet for the VADER lab. And then we also have a lot of joint projects. So one of our colleagues, Dr. Ariana Middle, who's with the Arts, Media, and Engineering program and joint with SIDSI, had this idea of what if we use Google Street View data to capture different parameters from microclimate simulations. Google Street View has captured all these images of the city, and one key factor for microclimate simulations is how much sky you can see at a given region. And so we took all those Google Street View images and stitched them together and calculated what's called the sky view factor. And this map with the blue and orange and red down here, the more blue, the more sky you can see. The more red, the less sky. So you can see these urban canyons. This is a picture of downtown Phoenix, so sort of showing the really open sprawl of Phoenix outside of this downtown urban canyon spread. But what's fun with this is we can think about, well, now that we know the sky view factor, we can calculate local microclimate simulations. We know the angle of the sun. We can calculate which parts of the street are in shade. We can use this for urban planning by capturing walking and pedestrian routes and seeing what time of day these routes are popular and thinking about if we need to add sunshades and these sorts of things. So lots of interesting things to do with this intersection between computer science, urban planning, and all of this data that's being captured. So that sort of gives you a little flavor of some of the things that go on in the Visual Analytics and Data Exploration Research Lab. We also have a lot of projects recently on explainable AI, fairness in AI, and I encourage you to visit our website, vader.lab.asu.edu. The other big center that I run is funded by the Department of Homeland Security. There's 10 of these different centers around the country, all focused on different elements. our center is the Center for Accelerating Operational Efficiency, where we're building advanced analytic tools to optimize efficiency in Homeland Security operations. So really we focus on data analytics, operations research, economic analysis, and Homeland Security risk sciences. For undergrads, we have capstone projects that are sponsored, working out of Phoenix Sky Harbor. We've had summer camps for collecting different data with the Transportation Security Administration. And what we're trying to do is support real-time decision-making through the application of advanced analytic tools. So I'm going to just talk briefly about a couple interesting projects we have going on in the center, but there's many, many more. One cool project First, let me talk about the three themes in the center for projects. The first theme is improving predictions to enhance preparation and response. So we're trying to develop new methods for high performance analysis of real-time streaming data. We're looking at creating predictive analytics tools, providing DHS operations capability to respond to situations faster. Another suite of projects focus on informing prevention policy through risk and cost analysis. So we're working on applying design science to conduct scientific inquiry while working to create system improvements such as enhancing aviation security at lower costs of operation. And then we've also been working on optimizing screening and border operations. So can we increase potential smuggling disruptions? Can we reduce illegal crossings and terrorist threats while not impeding legitimate trade and travel? So one of the cool projects we have going on in our center is run by Brandon Bellendorf out of the University at Albany on simulation analysis and modeling for border apprehension and security, or SAMBAS. And so what he does is he's identifying different hot paths of activity, leveraging existing U.S. Border Patrol data collection infrastructure. So we sort of know where people that are smuggling illicit goods have been arrested. And he's trying to sort of backtrace to guess the probable smuggling paths to think about how we can add more patrols or more sensors to better detect this and improve apprehension rate and increase operational controllability. So he's been creating different tools and apps to conduct initial route simulations for probable travel pathways, incorporate obstacles like physical obstacles such as rivers, ravines, mountains, things that would make it difficult to pass, and then look at conducting change detection to identify key changes from initial to secondary route estimations. So he's been building these tools for trying to do smuggling and interdiction. We also have a group at ASU, joint with folks at University of Texas, El Paso. So Professor Jorge Sefer leads this effort along with Ron Askin and Kelvin Chu, where they've been doing dynamic resource allocation for predicted demands at a network of screening facilities. And you can interpret this as we're trying to predict how many people come to the airport. And the reason we want to do this is because if we can figure out how many people come to the airport, we're hoping that we can better allocate resources to reduce passenger wait time without compromising security. So if we can create a quick and accurate passenger arrival estimation, we can do a proactive scheduling of the transportation security officers, and we can do better management of the pre-check and non-pre-check queues, as well as use this as an opportunity to train transportation security officers. And other interesting project going on with this is as you think about putting your baggage through the baggage screening, there's artificial intelligence that is telling these transportation security officers whether or not there's something that shouldn't be taken on the plane in your bag. And we want to think about how we can do this, develop this trust and automation for these TSOs, and how we can help them enhance their job through the use of artificial intelligence. And with this particular project, we've been doing this as summer programs and capstone programs where we had undergrad students going to the airport, collecting data on passenger throughput, as well as then coming back, taking this data and building these cool models and simulations. And we're really trying to understand the TSA field operations and practice, specifically that at Sky Harbor, and develop these sorts of simulation-based models to predict waiting times and queue lengths, and then develop a transportation security officer schedule to get the desired performance in terms of waiting time, queue length, and all those sorts of things, and then transfer this knowledge to end users. And so they've created this whole estimate of arrival curves, and we've delivered this to our partners at TSA. They even have an interesting simulation test bed where they're designing a 3D animation and allowing them to change different parameters to do different tests and train different transportation security officers in this sort of virtual environment. And in year 2, they're working on collecting more data at Phoenix, evaluating these models, and working on establishing a relationship with TSA at El Paso. And we've also been lucky enough to be able to do this at the University of Las Vegas in Nevada, working with the Las Vegas airport. And so this gives you an overview a little bit of our Center for Accelerating Operational Efficiency. We also have our Chief Scientist, P2 Merchandani. Dan McCarville serves as our Associate Director of Education. And you can find more information about the CAOE at caoe.asu.edu. So hopefully this gives you a very quick, very brief insight into some of the projects going on in the VADER lab and in CAOE. Would be happy to talk more, provide demos and things, so feel free to reach out. And that's all for today. Thank you.